It's the same as saying 7/3 to the n power. And in this case, well, this is what kind of series is this? It's geometric, convergent, or divergent, by the way? It's a divergent, right? This is a divergent geometric. All right. So this means that once we compute the limit, if we manage to obtain a limit that is positive and finite, well, then the original series will do exactly whatever the test series does. In other words, this series will also diverge. All right, so let's set up the limit. So that is limit a sub n over b sub n, where a sub n is the original series, the sequence related to the original series, and b sub n to the test series. Limit n approaches infinity, and that's 7 to the n over 3 to the n plus 9n minus 3 over 7 to the n over 3 to the n. And just make sure to delimit the quotients accordingly. That's so you can see how the division of these two expressions is going to be. So dividing by a fraction is the same as multiplying by the reciprocal of it. So this will be limit n approaches infinity, 7 to the n over 3 to the n plus 9n minus 3 times the reciprocal of this, which is 3 to the n over 7 to the n. All right, so at this point we may go about canceling 7 to the n. That's gonna, well, it's not a lot, but at least it's something to simplify, you know. And that's gonna leave us with limit n approaches infinity of 3 to the n over 3 to the n plus 9n minus 3. And well, let's go about this limit. All right. So there's a few ways to go about this limit. Number one is to, well, divide, like the calc one way to go about this limit. Number one is divide every single term by the highest degree or highest order term. In this case, higher order, because we have a combination of exponentials and polynomials. So really, the highest degree, which is n to the first power, is not big enough to divide out all terms. All right, so that's not going to do anything. In this case, we have to look at what's it called, the highest order function, which in this case is the exponential function. Well, but that's going to take a good minute to go about, a lot of writing. Well, there's another way to go about this limit. Number one, using the L'Hopital's rule. And yes, take the derivative of the numerator, take the derivative of the denominator, but I'm afraid in this case we would have to use the L'Hopital's rule twice to make sure that these two terms disappear, because we need to do one derivative to cancel out the -3, or rather to annihilate the -3, and we need a second derivative to annihilate the derivative of 9n, which is 9, which is going to be 0. So we need to do L'Hopital's rule twice, and that involves finding the derivative of an exponential function with a base other than e, which, I mean, we can review that, that's fine. However, in just the same way that we divided polynomial over polynomial, we just went with the ratio of the leading coefficients, you know, like when we have limit 3n squared over 5n squared plus 5n minus 1, for example. The ratio of the leading coefficients is 3/5, so that's the limit. As simple as that. Well, we can sort of have that when we have these exponentials, because check this out. This 3 to the n has an invisible 1 multiplying in the front, all right? And so the 1 in the denominator. So if we go with the ratio of the leading coefficients, I mean, ultimately the leading terms of the numerator and denominator are these exponentials. So we can just go about the ratio of the leading coefficients, which in this case is simply 1, all right? It's valid. It's a valid move. Back in Calc 1, well, you needed to understand how to identify the highest degree in the denominator, divide every single term by that highest power in the denominator. Yes, it was a little painful process, but that's to understand the algebraic techniques. Up to this point in Calc 2, well, I think we have a lot of tools in our toolkit. So in this case, I mean ratio of leading coefficients, because this problem is self-contained inside of a bigger problem. So let's just use those tools. So in this case, positive, finite. This means the series diverges, right? Diverges by limit comparison test, LCT for short. And again, make sure every time you are working with infinite series, make sure to state which test are you using. You know, even though the work sort of depicts, and gives the grader an idea of what test you're using, just make sure to state it at the end. All right. That being said, I believe this is the end of the section, so we may go about the next one. So that's 11.5.
I didn't see the note this morning.
Huh?
I didn't see a note.
Yeah, it was there. Actually, this is. So the next series, the next kind of series, the alternating series test and absolute convergence. Well, we're gonna look at every single point in its due time. Number 1. So far, we have worked with series that output only positive terms, all right? Well, except for those geometric series for which we have a negative common ratio that makes the sequence bounds between negative and positive, but we really didn't see those series as an alternating series, but this time will. And this is a really big group of series that contain this special factor -1 to the n minus 1. All right, that's how you can identify an alternating series. But of course, this is not the only option. There's other possibilities like -1 to the n, or even -1 to the n plus 1. All right, so either one of those three, that's for sure. Yes, that's an alternating series for sure. All right. Well, in order for an alternating series to converge, it has to satisfy two conditions. So we're going to focus on the B sub n, that is the sequence related to the series, to the infinite series, without the alternating factor. So number 1, if the limit of the sequence converges to 0, well, that's one of the first conditions. And the second condition is that B sub n plus 1 is less than or equal to B sub n. Okay, what is that inequality essentially mean? It means that the sequence related to the infinite alternating series has to be a decreasing one, you know? So that B sub n plus 1, which is the next term, notice it's telling you that it's smaller than the previous one, and that depicts a decreasing sequence in this case. Well, now why does that have to be a decreasing sequence? So let's do a brief picture of this. So number 1, a decreasing alternating series, it's going to look like this. You know, we start, for example, with a big number, alternates to minus, gets smaller every time, and eventually converges to 0, right? So that gets connected with the sequence converging to 0. All right? So I think the two conditions that's how these two conditions are linked. However, check this out. Check the increasing case. So we start with +1, for example, -2, +3, -4, +5, -6. Do you see how this is blowing up to infinity? Positive infinity or negative infinity? Well, so that's an increasing sequence. Well, that for sure it's going to blow up to infinity, and that's going to consequently give us a divergent infinite series. So that's why it's important. These two conditions are important. If one of these two conditions fail to be satisfied, well, the series diverges. Otherwise, if both of these two conditions are satisfied, the series converges. All right? So, let's go about some examples. So, let's determine whether each series converges or diverges here. So, sigma n equals 1 to infinity, negative of negative 1 to the n, 1 over n. So, the first condition is, letter I, that limit of b sub n approaches infinity, that is, limit of 1 over n as n approaches infinity, what is this limit equal to? 0. So first condition is satisfied. Let's go about the second condition, that b sub n plus 1 is less than or equal to b sub n. Alright? So, in other words, this is what we have to do for the original sequence 1 over n. Wherever you see the letter n, replace with n plus 1. That is 1 over n plus 1 less than or equal b sub, oh, not b sub n, just actually 1 over n. Is that inequality true? Does that mean that the sequence is decreasing? Yes. So the two conditions are satisfied. Therefore, the series converges by alternating series test, AST for short. All right? So that's our first example in the alternating series. Okay, let's have a look at another example. The next page, what do we have? Sigma n equals 1 to infinity, negative 1 to the n times n squared over n squared plus 5. First condition. The first condition states that, well, limit b sub n, as n approaches infinity, limit n squared over n squared plus 5, as n approaches infinity. But what's this limit equal to, by the way? Alright, so this limit equals to 1, which means it's not equal to 0. So in this case, the first condition is not satisfied. And no need to bother and check the other condition, because if one of the conditions already fails, the series already diverges. Now, connections with material from the past. Isn't that really like the n-term test for divergence? Where you get a number other than 0? What does that tell us about? It tells us that it diverges, right? So here is a good connection with that test from that we saw before. So we're done with this example. That's it. No need to check the second condition. All right? All right. Let's see. Let's look at another example. Sigma n equals 2 to infinity, cosine n pi over the square root of n. Well, doesn't look like an alternating series, does it? But it is, exactly. It is an alternating series in disguise. However, okay, let's rewrite this series. So how about we expand some of the terms of the numerator just so we can see a pattern. So that is cosine of 2 pi, because we start at n equals 2. So cosine of 2 pi, isn't that what's that? It's 1. What about cosine 3 pi? That's 0. Negative 1, right? What about cosine 4 pi? 1, negative 1, 1, negative 1. So the pattern goes from negative 1, 1, negative 1, 1. It's, well, I mean 1, negative 1. So it's alternating, right? So this cosine n pi, it's an alternating factor in disguise, right? So let's rewrite this series n equals 2 to infinity. And well, so let's see if negative 1 to the n works. So starting at n equals to 2, what is negative 1 to the second power? Is that positive 1? Yes, so we don't need to add a +1 or -1 in the exponent of -1, all right? So we're good to go with the alternating series test. So number 1, or letter I, all right? Letter I, that's the limit b sub n approaches infinity of, well, limit 1 over the square root of n over n, as n approaches infinity. All right. What is that limit equal to? 0. So the first condition is satisfied. All right. Second condition is the sequence related to the series a decreasing sequence. Well, let's find out. Is 1 over the square root of n plus 1 less than 1 over the square root of n? Is that inequality true? It is, because, well, what do we have on the left-hand side of the inequality? We have an n plus 1. That's going to make us divide by a slightly larger number. And when we divide by a larger number, that's going to, the end result, it's a smaller number, which is really smaller than on the one on the right-hand side. So, yes, the inequality is true. So both conditions are satisfied. And in this case, the series converges by alternating series test, AST for short. All right? Yes.
Can you explain what the cosine is?
Yes. So this one is really this cosine or sine typically bounds between -1 and 1, you know, so depending how they're arranged. So what I did here is to focus only in the numerator and expand some of the terms of the sequence only for the numerator, so we can see this pattern: 1, -1, 1, -1, etc. So starting at n equals to 2, cosine of n pi, which is cosine of 2 pi, that's 1. Cosine of the next n, which is 3. Cosine of 3 pi, -1. Cosine of 4 pi, +1. Cosine of 5 pi, -1. So in this case, what we're seeing here is the alternating factor: 1, -1, 1, -1. So we really rewrite this cosine n pi as -1 to the n. All right. So it was hiding in this alternating factor was hiding in this guys as a trigonometric function. All right. Looks like that series is ready for Halloween, right? So, okay, what else do we do about this alternating series? Well, so here is the thing. This alternating series contain terms that are positive and negative. So what we're going to do is create a whole new problem. So we're going to take the absolute value of the series and study a new problem, a new series that for now won't have anything to do with the original alternating series. So you may forget about the alternating series for a few minutes and focus on a new series. So we will check the new series, and if that new series converges, then the original alternating series will converge absolutely, because that series converges both in its alternating form and in its absolute value form. However, if the new series that we obtain after taking the absolute value that happens to diverge, well, that series, the original series, the alternating series will diverge. Will not diverge, will converge, but conditionally. Why is it conditionally? Well, it's conditioned to converge only in its alternating form, but not in its absolute form. I guess some examples doing some examples will be a lot better. And actually, I have this flow chart for you. Hopefully, it's helpful to see the roadmap about alternating series. So. And again, let's review what we have done so far. So we're given this alternating series, which is, well, sigma -1 to the n, or -1 to the n plus 1, or -1, whatever, b sub n. So in order for this series to converge, these two conditions have to be satisfied. Number one, the limit of the sequence converges to 0, and the sequence related to the alternating series is that of it's a decreasing sequence. All right. If one of these two conditions fail to be satisfied, well, diverges and we're done. We don't have to do anything about this series. We're done. However, in the convergent case, we still have to go the extra mile. Number one, to check absolute convergence or conditional convergence. And that happens, well, absolute convergence happens when the absolute value of the series, which creates a whole new series, is convergent. And conditional convergence occurs when we take the absolute value of the series, and that new series, it's a divergent series. So let's have a look at one example or a few examples actually, in which we will check whether the series converge absolutely or conditionally. So number one, we have to check the two conditions. So that is limit -1 to the n plus 1, actually without the alternating factor, well, what is this limit equal to? 0. First condition is satisfied. Second condition, limit, not limit, so that's 1 over n plus 1, quantity squared, plus 8, less than or equal 1 over n squared plus 8. Is that inequality true? Yeah. It is, because that quantity that gets squared is increased by 1, so for sure that's going to give us a larger value in the denominator of the left hand side of the inequality, making an overall value smaller than indeed its right hand side. Alright, so this is true, this is true. We're good to go. And find the absolute value of the series. So this is what we're going to do. Sigma n equals 1 to infinity of the absolute value of -1 to the n plus 1 over n squared plus 8. Alright? So, well, what happens when we take the absolute value of that expression? Well, number one, see that alternating factor? -1 to the n plus 1. That's going to output a bunch of -1s and +1s. But since we are taking the absolute value, what's going to happen to those negatives? They're going to become positive, right? So by taking the absolute value bars, that cancels out the alternating factor, and this is equal to sigma n equals 1 to infinity. And without absolute value bars, just write 1 over n squared plus 8. And that's a whole new problem. Forget about the alternating series for a second, for a few minutes actually. So let's focus on this series, and let's see if we can find the convergence or divergence of it. So number one, well, that's definitely not a geometric. Well, it looks like a p-series, but it's not directly a p-series, right? So, but we can use comparison by comparing with a p-series in this case. So compare with well, neglect the 8, n equals 1 to infinity over 1 over n squared. Well, what do we know about this series? Would it be a convergent or divergent p-series? It's a convergent p-series, right? And you have two options. Number one, you can do the direct comparison or the limit comparison. But I think the direct comparison in this case is going to be a lot quicker. And again, when it comes to direct comparison test, when we compare with something that converges, we need to show in this case that tiny is less than or equal to small. In other words, a sub n less than or equal b sub n, where a sub n is always the original problem, 1 over n squared plus 8, less than or equal 1 over n squared. Is the inequality true? Well, in this case, it's true that tiny is less than small. So for this reason, okay, here is where we are going to go, where we will backtrack to the original problem. So number one, the absolute value of the series converges by direct comparison with sigma n equals 1 to infinity 1 over n squared. And then because the new series converge, the original alternating series converges absolutely. All right, converges absolutely. All right. Okay, let's check with the diagram here, with the flow chart that we have at the top of the page. All right, so again, we checked the two conditions. This series met the two conditions for convergence, so we went the converges route. From here, we had two options. Number one, to converge absolutely whenever the absolute value of the series of the absolute value converges, which was the case in this time. All right. Let's have a look at another example and see what happens, see how it works. So what do we have? Letter B. Sigma k equals 1 to infinity, negative 1 to the k, ln of k over k. So the first condition, limit ln of k over k as k approaches infinity. All right, let's find out about the limit. So number one, what do we have? Well, this limit is not just 1 over expression like the previous ones we have done for a while. In this case, we have k's, we have variables on both numerator and denominator. So in this case, we will have to try direct substitution, but unfortunately, it's not going to give us a 0 right away. So ln of k at infinity, that's going to be infinity, and divided by k, which is also infinity. This means infinity over infinity, which is great. This means we can use any algebraic technique available, like factoring, rationalizing a numerator, denominator, multiplying numerator and denominator by a conjugate, divide all the terms by the highest degree in the denominator, but I don't think this is going to be a good idea, you know, so...
Isn't it grow faster than
Yes, that's what we're going to analyze later when we check the decreasing part. So in the meantime, since none of the algebraic techniques work, our plan B for this is L'Hopital's rule. All right, so let's do L'Hopital's rule for, that is, limit k approaches infinity, and the derivative of ln of k, that's 1 over k, and the derivative of k is 1, which is really the limit of 1 over k as k approaches infinity, and this limit happens to be 0, which is, well, first condition is satisfied, right? The second condition, all right, so b sub n, or actually b sub k plus 1, which is not n this time, it's k, less than or equal b sub k. In other words, it's the sequence ln k over k, decreasing sequence. Let's find out. So, ln of k plus 1, shifting the left-hand side by k plus 1 over k plus 1, less than or equal ln of k over k. Is this inequality true? Well, at first glance, it may not look like it because, well, let's observe the numerator here. So what do we have on the left-hand side? ln of k plus 1 versus ln of k. Well, that ln of k plus 1 on the left-hand side for sure is going to be a larger value than the one on the right-hand side. But do you see the inequality sign? So that's like that's telling us the opposite. However, so just like you mentioned earlier, actually the k, the denominator k, which is a polynomial, is a function that grows faster than the logarithmic function, and you can rank the functions. You can make a table of values so you can see how the function y equals x versus y equals ln x, the function y equals x grows faster, or simply with a graph. I mean, check the graph of natural log, which looks like this. Check the graph of y equals x. I mean, think of infinity. I mean, which function is growing faster? The linear or the logarithmic?
The linear.
The linear, right? So what do we have? Larger denominator, smaller numerator. This one has to be true. Alright? So this inequality is true. So the two conditions for convergence are satisfied. We may go ahead and take the absolute value of the series k equals 1 to infinity, absolute value of -1 to the k, ln of k over k. Well, and again, taking the absolute value of something that contains alternating factors, that cancels the alternating factor, and we're left with only the general rule, ln of k over k. So no more alternating factors, no more alternating series. We have to forget about them for a while. So let's focus on this series ln of k over k. Well, not a geometric series, not a direct p series, but we could use a p series actually to compare with this series actually. So we can compare with sigma k equals 1 to infinity of 1 over k. And this series, which is a simpler series, it's a divergent p series. Okay? So, as opposed to the previous exercise for which we also used the direct comparison, for the previous example, we had to show that tiny is less than small, but that's because we're comparing with a convergent series. But in this case, since we are comparing with a divergent p series, we have to show that huge is greater than or equal to big. That is, the original problem a sub n is greater than or equal b sub n, which in this case is ln of k over k. Is that greater than or equal 1 over k? Well, yes. I mean, I think this is pretty straightforward to see because, well, you can cancel the k's if you want. You will be left with ln of k. And, well, for large values of k, well, ln of k, ln of infinity is basically infinity, and infinity will always be greater than 1 because the right-hand side will always remain 1. That doesn't change. So this inequality is true. This means that the series diverges by direct comparison test, and backtracking to the original alternating series, this series converges, not absolutely, but conditionally. Alright, so converges conditionally.